talk about joining arrays. Okay, so there are two ways essentially to join an array. The first one is concatenate. And the second one is stacking. So let us first look at concatenate. Let me define two arrays. Right, note that they both have the same shape. Now if I do np.concatenate, let us first look at the documentation. So here you give a tuple of arrays that the tuple should contain the arrays that you want to concatenate. Then you also give the access, right? So these are the two important uh, um, inputs here. So access is equal. So we'll let's now write the code. So and while I do it, I'll explain what access is. So access essentially for an n-dimensional array, right? If you give access is equal to 0, then you would be joining in the nth dimension. Then if you give access is equal to 1, then you would be joining in the n minus 1th dimension. And then if you give access is equal to 2, then you'll be joining in the n minus 2nd dimension. We will see how that works. Okay, so then we'll give A1 and A2. Now the only option that we have here is to give access is equal to 0, because this is a one-dimensional array, and if you give access is equal to 0, if you give access is equal to 0, the join will happen in the first dimension. Sorry, excuse me 1 second. Right. So this is what we get as an output. The two arrays have been joined in the first dimension because we give access is equal to 0. We cannot give access is equal to 1 here because uh, there is no n minus 1th dimension, that becomes 0. We cannot join in the 0th dimension. So the only access that we can give here is 0. Now if these were two-dimensional arrays, right? So if let's say these two are two-dimensional arrays. Okay, and both A1 and A2 are two-dimensional arrays, and now if I were to do this with access is equal to 0, they'll be joined in the second dimension. So that would mean that you'll get 4 one-dimensional arrays inside a two-dimensional array. Okay, so that is exactly what you get. So they have been joined in the second dimension, and you're getting all 4 one-dimensional arrays are now a part of a single two-dimensional array. Now if I change the axis is equal to 1 here, which is possible because there are originally 2 dimensions in the arrays, the original arrays that we have. So you can give axis is equal to 1, and that means that they will now be joined in n minus 1th dimension, which is the first dimension. So let's see how that works. So you can see that now they've been joined in the first dimension, and 1 and 2 have been joined to 5 and 6. Right, so they have been, these two arrays have been joined in the first dimension to get a bigger one-dimensional array, and same with these two. Okay. Now you cannot give access is equal to 2 because that is out of bounds. Alright, and if these were three-dimensional arrays, then you can give three axes 0, 1, and 2. Okay, the zeroth axis will join the arrays in the third dimension. The first axis will join the arrays in the second dimension, and the third axis will join. Second axis will join the arrays in the first dimension. I hope that makes sense to everyone. All right. So I want you to solve this, right? So if A1 is, let me copy this. So currently it's a two-dimensional array. Now what if it was a three-dimensional array? Okay. So I want everyone to tell me what would be the output of this and this and this. I want you to type the output in the chat. Okay, I'll give you a few minutes. is equal to 0, you get a three-dimensional array with four two-dimensional arrays. Okay, and basically the joining is now happening in the third dimension. When you give access is equal to 1, um, you are getting only two two-dimensional arrays because the joining is now happening in the second dimension. So the second dimension, these two arrays have been joined to form a single 2D array, and these two have been joined to form a single 2D array as well. So you're getting two 2D arrays, and the joining has happened in the second dimension. And when you give access equal to 2, the join now happens in the first dimension. Okay, so you get 1, 2, 9, and 10. So essentially, these two arrays have been joined to form a single 1D array. These two arrays have been joined to form a single 1D array, and so on, right? So you get two two-dimensional arrays within a three-dimensional arrays, and each two-dimensional array has two one-dimensional arrays with four elements each. Okay, so this is what you get as an output. So I hope this is clear to everyone. Concatenation. It's an important topic, and if this is clear, then you're also clear about all the things that we discussed yesterday, the shape and dimensions. Uh, so yeah, if you understand this, I think that you are mostly clear about arrays and their shapes and dimensions. Okay. Now the next is stacking. Now, stacking can be of actually it can be of three types, right? The stacking can be of three types. Uh, it can happen. Actually, the stacking can be of multiple types, but uh, there are specific methods for three types of stacking uh, in Numpy, and these methods are V stack, H stack, and D stack, and then there's a generic stack method as well. So we'll start with V stack and H stack, right? So if I do np dot V stack, right, this stands for vertical. V stack is basically short for vertical stacking. So if you want to vertically stack two arrays, then they will come one below the other, like this. Vertical stacking, as the name suggests, is stacking the two arrays one below the other. Then you have edge stack. Edge stack means horizontal stack, and this is for stacking the arrays next to each other. So, so with vertical stack, you're getting a two-dimensional array, but with horizontal stack, you're getting a single-dimensional array. Now, there's another thing called D stack. Now, D stack is depth stack. The depth stack is going to give you a three-dimensional array, and it is going to stack them in the third dimension, which is depth. So vertical, horizontal, and depth. So D stack is going to now give you a three-dimensional array like this. So now this is a three-dimensional array, and these two arrays are now stacked in the depth dimension or the third dimension. Okay, and then you also have a generic stack method, right? So you have np dot stack a1 and a2, and then you can give access is equal to 0. If you give access is equal to 0, you get a vertical stack. Now here access has a totally different meaning. Access is equal to 0 is for the vertical axis, access is equal to 1 is for the depth axis, access is equal to 2 does not exist. How do you horizontally stack that? The access in the result array along with the input arrays are stacked. So how do I get a horizontal stack? Here, they're joining in the first dimension There's no way to do a horizontal stack with the stack method or what. Like if one, then you and two is not there. I don't know. Axis. How is the axis defined here? It's I'm not even sure. The axis parameter specifies the index of the new axis and the dimensions of the result. For example, axis is equal to 0 will be the first dimension, and if axis is equal to -1, okay, you can also give -1. Last dimension. So this is the same as giving axis is equal to 1 in this case. Okay, I get it now. So axis is equal to 0 will be the first dimension and axis is equal to -1 will be the last dimension. Now here, for A1 and A2, A1 dot shape is 4. So when I do 0, just act like this, one below the other. This is weird. I'll do more research on how stack works because currently I'm not able to wrap my head around this. How is the axis working here? Like, what does this even mean? If axis will be the first dimension, axis parameter specifies the index of the new axis in the dimensions of the result. The axis in the result array along which the input arrays are stacked. So if axis is 0, the input arrays are stacked in what? First dimension. Okay. Here they are stacked in the first dimension. Okay, and here they are stacked again in the first dimension. They're stacked in the they're very weirdly stacked. Okay, we will get back to stack probably later. I'm not able to wrap my head around the axis for now. Okay, let's move on to but I hope you've understood B stack, H stack, and D stack, uh, and also concatenation, and that should be enough for all practical purposes. You don't even need to use stack. Um, so yeah, let's move on to something called split now, which is the opposite of stack, right? So split, this method is actually the exact opposite of uh, uh, stacking or joining, right? So this is our A1. The method is called array split, right? So if I do np dot array split, and you have to give your array here, and you have to specify how many splits do you want, right? So yeah, if you're splitting it into two, you're getting two arrays which look like this, right? And you can also split it into three, although it has only four elements. If I split it into three, the last two elements, the last two arrays will have only one element, while the first array will have two elements, right? So it's not necessary that uh, this should be divisible, the length of the array should be divisible by the number of splits. That's not necessary. Now, let's take up a 2D array. Um, or let's take up a Now let's do the same thing with this. I don't think you can fit 3. So splitting into 2 is straightforward, but you essentially, if you split it into 2, you get 2D arrays. Remember that. You don't get 1D arrays, you get 2D arrays. Okay, if I do it into 3, the third array is now empty. So third array that I get is empty. Um, Now, if there are 4 1D arrays in the 2D array, the first array will have 2 elements, and the remaining 2 arrays that are returned after the split will have a single element or a single 1D array. Now, even this takes access. So I can specify the access as 0. I get the same thing. If I specify the access as uh, uh, 1, then you are splitting in the first dimension. So if you are giving access equal to 0, then you split in the second dimension. But if you give access is equal to 1, then you are splitting in the first dimension. So basically this is the opposite of concatenate. Now the split has been made in the first dimension. So 1, 3, 5, 7, they are now present in the first array. 2, 4, 6 and 8 are present in the second array, and the last array is empty. If you not give access is equal to 2, give only 0 and 1. Right, so if I now take up a 3-dimensional array like this, right, so now I have a 3-dimensional array. Now if I give access is equal to 0 here, it is split in the third dimension. So we now have 3 arrays, and the first array you have 2 2-dimensional arrays, right? So the first one will have these 2 2-dimensional arrays, and then the remaining 2 arrays will have 1 2-dimensional array, which will be this and this. So that is what is returned here. If I give access is equal to 0, if I give access is equal to 1, now the split will happen in the second dimension and not the third dimension. The split happens in the second dimension. This array is split open, like this is the 2-dimensional array, right? This is split open into this, and this is joined with this and this and this, right? So that forms your first array, right, which is here. Then the second array will consist of this, 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 and this. So these are all 1-dimensional arrays, and that forms the second array. The third array is empty. Okay, the third array is empty here. This is access is equal to 1. Now if I give access is equal to 2, the split will happen in the first dimension. So these two will be split. So one array will contain this and the other one will contain this. So that is exactly what has happened. So the first element of each 1-dimensional array has been put into a array, and that is the first array that is returned. Then the second array contains the second element of each 1-dimensional array, and finally the third array is empty. Okay, so this is how the split happens in the third dimension. So I hope this is also clear to everyone. Next, we can look at conditional indexing and searching. Okay. So how do you do conditional indexing? Let's say you have A1 which looks like this. No. Let's create a simpler array here. This is our, and this is the array, and if I write a condition like this, A1 greater than 4, okay, so I get the first four elements, I get a new array where the first four elements are false and the last four elements are true. Okay, uh, so this is what happens when you write a condition like this. Now, if I were to filter an array with another array which contains true and false, so if I make one of them false, rest of them are true. So you can see that originally there were 8 elements, and I indexed the array with another array of true and false, and one of the values was false in there, and you can see that that index, right, this is the second last index, so the element in the second last index has not been returned. So essentially, if you give a binary true false array as an index to a numpy array, only the true, only the values in the index with true are returned. So you don't get 7 here because that value was false. Okay, so that means that I can do this also. I can directly do this, because this returns an array with true and false, and this accepts an array with true and false. I can directly write it like this, and that becomes and this essentially is called conditional indexing. Okay, I can keep doing this. I can say a1 percent 2 is equal to 0. If I do this again, I get a true and false array, so I can again give this as a condition, and this also works. Then I can also do this. It works with an ampersand. Yes. Okay. So this, if you do this, this ampersand is the symbol for AND gate, which NumPy uses. So NumPy you can't directly write A and B. You have to use the symbol called ampersand. Okay, and then you can give this as an index. Uh, and there's another logical symbol here, which is this. This is the OR symbol. Or this pipe symbol is basically representative of the OR logical gate, and yeah, here the number is greater than 4, or if it is divisible by 2, then it is returned. So 2 is also returned in addition to 2, and 4 are also returned in addition to this condition being satisfied. Okay, this is the OR gate, this is the AND gate. So I hope this also makes sense. Um, Now, um, yeah, we can also search So the keyword which is used for searching is called where. So if I do this is A1 right now. If I do np dot where, and then I have to give a condition here, right? So the condition could be anything. It could be an exact uh, A1 is equal to 4. It could be something like this. So you get the index of the element where the value is 4, right? So A1 is equal to 4. This will return, let's see what it returns. It returns this one true and the rest of them are false. And where essentially uh, returns the index of the true elements here, right? So if you give where an array with so inside where you're essentially giving a binary array with true and false, and where is simply returning you the index of the true values. Okay, so you can give a complicated condition also here. Percent two is equal to 0, and what you get is you don't get the array as it is, so you're not getting this. These are the values. What you're getting is the array with the index of these elements. So if you want the index, then you'll use where. If you want the elements, then you will directly go and index. Okay, that is basically uh, what where is used for. All right. So this is searching. Uh, yeah. Then you can also sort the array. So if you have an array which is not sorted, what it looks like, uh, then you can simply do np.sort and give one here and sort it for you. Now, what happens with a 2D array? So if this was a 2D array, then uh, you would have seen that uh, the only the so sort will only sort the values in the first dimension. It doesn't matter if your array has 2 dimensions or 3 dimensions or 4 dimensions. Only the individual one-dimensional arrays will be sorted, and nothing else will change. Okay, so sort will only sort the one-dimensional arrays and not change the uh, remaining structures. So here you can see that this one-dimensional array was sorted separately and this one-dimensional array was sorted separately and nothing else changed. Okay, and this will hold true for 3, 4, and 5 dimensional arrays also. Right. So now let's take a break. We'll restart at 10 o'clock. Okay. Uh, there's there are a few things which remain in NumPy. How to use NumPy functions, and the second thing is there's a random module in NumPy which is also useful sometimes. So we'll cover these two topics after the break. Okay. We'll restart at 10. So we're going to look at the functions in Numpy. So let's look at the basic arithmetic functions. Hmm? Like sum, or in this case it's called add, right? So you have a1, let's call it x and y now. And y, and if you do np dot add and you get x and y here, so they're basically added in the first dimension only. So, so basically this is an element wise addition. Okay. Um, Similarly, you have element wise subtraction. And the method is np dot subtract x and y. Let's subtract x from y. So you'll have to give y and x. Give y and x. Yeah. If I give y and x, I'm getting 4, 4, 4, 4, 4. If I would have given x and y, I would have gotten minus 4, minus 4, minus 4. Then you have element wise multiplication. I cannot cover all the methods that is there in NumPy. A lot of them. Okay. So you have, I'm just going to give you the most simple ones. There's multiply and there's divide also. Let's divide y by x, right? So there's divide also. Um, a lot of other ones like np dot mod. Now mod gives you the remainder of, so this is basically when you're dividing y by x, mod will give you the remainder of when y is divided by x. Okay. Uh, then you can take an array like for example this, and you can convert it to a logarithm. You can say n p dot log and give x here. That is converted into a log at base e. So this is log at base e, which is, you also know it as the ln function, right? Then you can convert it to np log 10 and then give x. So now this is the logarithm at 10. Okay. There are a lot of methods actually. I cannot cover each and every one of them. Okay, I cannot cover each and every one of them. You have trigonometric methods also, for example. So you have np dot sine of 180, right? Um, no, actually this takes in radians. This does not take in uh, degrees, it takes in radians. So you'll have to give pi. So pi is also there in np, so you'll have to do np dot pi. Right, so this is a very small value, almost equal to 0. This is actually 0. right? Mu NP pi by 2, that is 1, uh, and cos, tan, even the inverse functions are there. There's a function called NP dot radian to degree, okay, rad to dig, and you can give NP dot pi here, and returns 180. Okay, all kinds of, there's so many. It's impossible to cover all of them. For example, this Pythagoras theorem is also implemented here. So you can say that I want the hypotenuse, so the NP dot hypotenuse, NP dot hypot, and for 3 and 4. So it will give you 5. Okay. Then distributions are also there. Uh, for example, you have the uh, uh, normal distribution and binomial distribution. These distributions are also there in NumPy. Yeah. One more thing that I should tell you is that how to create your own custom NumPy function. So you can create a function as usual. And then creating a function add user, whatever, like user created add function. It takes in two elements, x and y, and simply returns plus y. Now this is not a NumPy function. To convert it to a NumPy function, right? You'll have to do this. Add user NumPy would be, I'll have to use this NumPy method called from py function. It's called from py func. This method takes in three arguments. The first one is the name of the function that you want to convert to a NumPy function, add user, and then it takes in the number of arguments that this function is going to take. So it takes in two arguments, and how many values is it going to return? So it will return a single value. These are three arguments that this function needs. Once you do this, now this becomes a NumPy function. Okay, so you can take this and give x and y, which are the two arrays that we created, and you can see that they have been added element wise. This is how you create a custom function, right? Now the number of NumPy functions are huge, so I cannot cover all of them, but you can go to the official documentation and search for functions. Actually, that's, yeah, mathematical functions. See that there are a lot of them. Okay, so you have these mathematical functions. Then you have a matrix library also. Uh, there are actually a lot of methods here. It's just impossible for us to cover everything. So we have a basic idea now, right? We have a basic idea of how uh, there are Fourier transformations. Uh, um, then you have then you have a lot of matrix methods. Um, then you have this statistics. So you get the statistics also. You can get mean, percentile, quantile, whatever, right? A lot of statistical methods are also there. Um, yeah, this is the linear algebra library. So the linear algebra library is the most important library, I would say. The linear algebra can give you the dot product of two arrays. So I could say np dot and then give x and y here. This is the dot product of x and y, right? If you remember the formula for the dot product of two vectors, uh, it's you do an element wise product and then sum that up, right? So essentially it's the sum of the element wise product that gives you the dot product, right? Then you have the inner product and the outer product. This is like the dot product, right? Inner and outer dot product. Then you can also have the eigenvalues. There are decompositions in linear algebra. Like I don't even know what is a Cholesky decomposition, but it is there in Numpy. Eigenvalues I know of, so you can also find the eigenvalues and the eigenvectors directly. Then the norm of the vector, um, and so on. There are a lot of things that you can do, right? So what I want you to do is, I'm not going to get into each and every method that you have in NumPy, but you should probably do it once. You should go through this documentation and look at the different things that you can do with NumPy. Okay. Documentation. So we have looked at how these methods are used. I cannot cover all the methods. Alright. Now there's a sub-module in NumPy which is called random. Again, something that is used often, like the random module. So the random module contains some basic methods which are often useful. I'm going to just cover those basic methods. Um, so, um, um, np dot random dot, what it is, random integer. To generate a random integer, we'll do random int, and then you will specify the uh, lower and the upper bound. So you can also specify the upper bound only. So let's say I specify the upper bound at 10. So I'll get a integer between 0 and 10. Then I can also give the shape here. So I can give the shape of the, so shape means that what do I want the output shape to be. So I can create a matrix also here. So I want a 4 by 4 with size. So size specifies the size of the output array that you want, and every individual value will be an integer between 0 and 10 here. Okay, so you can create either a single integer or it could be an array. Right? There's another method called uh, RAND, which gives you a probability value. This method is going to give you a value between 0 and 1, essentially a probability value. And then again, you can specify the size here. Cannot specify the size. Achha, you don't, it's directly, you have to give it directly here. Yeah. Okay. So then you have a method called choice. Now this takes in um, an array. or a list or whatever. You give a list here, and it will randomly choose an element. Every time it will randomly choose an element. Now here you can also give size. So if you want to choose elements randomly and create an array of a specific size, then you can do it, right? You can also give one more thing, which is the probability value. So you can choose your own probability values. You can say that, okay, I want the probabilities of choice for all of these elements to be different. So let's say you want 0 probability, 0 probability, 1 probability, 0 probability, 0 probability. So every time, so only 3 is stored because the probability is 1. Now I can update these probabilities. Uh, but they should all add up to 1. They should add up to 1. 1, 2, 3, 4, 5, 0.5. Now 8 has a very high probability of being chosen. The rest of them have a smaller probability. You can also see that if you want. Okay. Now there is another method called uh, shuffle. So you can say my x, I could say np dot random dot shuffle x. Now x is shuffled randomly. Okay. Uh, um, yeah, I mean that should do it. I think that should do it. In this library, you can also generate distributions. So one more thing that we can cover is how to generate these distributions. We can say that I want a normal distribution and I want 100 values. Uh, okay, so not 100, no, the size to be. So you get an array, and if you were to plot this array, okay, if you would plot this array, you would see that this is actually a normal distribution. We can plot it if you want. Let's let's actually plot this. Um, if not seen C1, don't worry about it. It's just a plotting library, and I'm just trying to plot a distribution plot. This is a normal distribution, almost normal distribution, right? If I were to increase this to, let's say, 1000, it would look more normal. 10,000, even more normal, right? Other distributions are also present. You can check them out, but not in your syllabus. Binomial, Poisson, uniform logistic, all of these distributions you can create with Numpy. So basically, you can also create such distributions as well with Numpy. That's what I wanted to show. Okay. So with that, uh, yeah, with that we can say that we have covered most of the topics in Numpy. I think it's done. Um, so um, yeah, if you have any questions, you can ask me now.